Okay, so now I am about to uh, improve the recognition of kata hiragana and katakana in the kana stats thing. Right now, I'm doing some hacky stuff to just look for distinguishing bytes in the katakana hiragana characters, and that's kind of silly. I would rather not do that. So, but I'll still continue to do some silly stuff. So, if the byte is E3, we just skip. So we can do like here int c. So let's do char buff 3, and I think I have xf read in util. Edit util.h xf read, and xf read. Right. Oh, and by the way, actually, maybe I have a better idea. Kana util, edit kana util test. I think maybe I forgot something. And why am I not able to edit kana util, kana stats, kana util test? There. I didn't do any stat lines that have both hiragana and katakana. So just for completeness sake, let's do that. Let's just say 12-digit hira and kata count, right? So we'll do 1, 0. So let's see here. Yeah. Okay. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And just to make it interesting, I guess from here it's 9, and so we can, on the 5th digit, 1, 2, 3, 4, 5, we can replace this with 8, and replace with 7. All right. Then, yeah, let's make that and see what happens. Buff 3. Okay. Edit kana stats. Let's see what happened here. Index not found. B search test. All kana count is too low. Why did it get a B search test failure? J1. Okay. All right. Anyway, I'll probably figure that out later. Cut. Edit. Input. Okay. So we'll do mul. And make kana stats util tests. Let's run that directly. Well, kana count is too low. Okay. Edit kana stats util. It's too low. What happened there? Oh, right. I don't want to make that 8. I want to make that a different number. That should be low enough. All kana count is too low. 4, 2, 1, 1. Why? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. 4. So 1, 0, 0, 0, 1, 0, 0, 0. 4, 2, 1, 2. Okay, I guess I can see why that would not work. Let's just change this to 3. See, at this point, I just test the math that the computer's doing. So here we go. Okay, this all looks correct. So if we do, let's see here. Let's just make sure the percentages are correct. So we'll do divided by that. That is 79.3052. And yes, you can see that's correct. So we'll also try this one. All right, so that's 18.8301. 8303 rather. Yes, okay. And then you add those two together. All right. And divide by 4 again. It should get the final value, 24.537. Yes, correct. That matches down here. Good. So now we can just do a copy. I'm lagging a bit. Let me kill a bunch of browser windows, I guess. Check for this. Okay, let's try that again. Okay. Right. Okay. Kana stats test is failing, as we would expect. Okay. So kana stats test. Okay, kana stats test mix two chars. Mode that test out. Oh, that's not correct. Hiragana is 1 and no katakana. Right, and 100%, 100%. Okay. Now we make right. Need to copy it now, not, and then there we go. Okay, so make. Now we see the diff. And right, so now we can go to kanastats.c, and let's just try even harder to get the to get a crappy hacky thing. So int last c is 0. Okay, yeah. So do last c equals c here. And say if last c is 0 by 82 and c is 0 by 82, then we can do mole count plus plus. Okay, int mole count is 0. Okay. Okay, so then this is probably not going to work because we didn't do the total diff. Okay. So, and the total is incorrect. Let's edit that. Expect to test out. Right. Yes. Make diff. Okay. Okay. I'll do a plus mole count here, and that should make the final line correct. Make 1. Okay. Nope, not quite. Total count. Total plus equals mole count. Let's see. If last c is a2 and c is a2, then mole count is plus 1. It's not working. Echo what is the input? Did I not write the input file correctly? Test input, kana stats test, hiragana mo. Okay, let's see that file. 8282. Okay. Oops. Why is that not working? Kana stats.c. So we have if last C is 82 and C is 82. Oh, but C is not signed. It's not going to be negative. So that's not a problem. Last C equals C. 2 more count. Total. So total is a count plus total count. Oh, because it's not adding it here. So total. Okay, let's see what happened. Okay, good. So now we do if mo count, then do this. Okay. Oops. Mo count, and this is 0. Let's try that. Good. This is a pretty silly test, and a pretty silly way to get it working, but it's fine. So now how can we break that? How can we break that hacky approach? So mo really is 82 and 82. Now we could find a kanji character that has 82 in it, two 82s like that. So printf x e2 x82 x82. That was e. That was mo. Oh no, it wasn't. So okay. Now we can try what happens to do 4. Okay, that's an interesting character. So we have a real character here, not a common one, but it works. So let's go to edit test. We're going to make a new test. Edit kana stats util test. Right? Oh no, kana stats test. UTF-8. Oops. Oh darn. In UTF-8, this character. No. Copy and paste. This has 282 bytes as well. Okay. Test. So now we have shares 2 bytes with hiragana mo. Okay. Okay. Let's copy and paste again, and see how that works out for us. Okay. Right. So, but really what we want is we want the empty output to match this. Kana stats test. Or wait. Kana stats test dot c dot shares empty input. Copy that to expected test out slash this. Okay, diff. Now the diff should look correct. Right, okay. Kanji shares. Now, we can go ahead and do, let's see here. We have kana stats. Let's see. Now, how asinine do we want to get about using hacky logic? So we can do another last C. And we just have a running like 3 bytes that we just go through. But then how do we actually compare? So that's, I think we don't really want to use 3 C bytes. We want to use like a buffer of 3 bytes. Last C. Let's just see how this works. Last C. Then we do last C equals last C. If last C is hereby 8, 3, end. Okay. Okay. Good. So and test input shares 2 bytes with hiragana mo. Wait, what happened? I thought I already wrote that file. Oh, right, I changed the name of the test again. So I have tear shares 2 bits with, all right. Kanji shares 2 bytes with hiragana. Okay. And do the same thing for test input. Boy, it's a pain. Pain to have to fix this after the fact. So that's kanji. Okay. All right, good. So that was hideous. Now we can also mess up the a count, hiragana a. So we can do hex dump dash c. Okay, 83, 81, 82. Now if we change 82 to 83, that's E. Here. Okay, 84. Right. Okay, so we can do UTF-8, E shares the first 2 bytes with A. Okay. Hiragana E. Okay. Just to make so. Okay. Gotta create the test file. All right, test out. Okay, no. So we do want this to be E, don't we? Make kana stats test. Right. And right. So we oh, I did the wrong thing. I edited the file, then I overwrote it. Let's try this again. Okay. Now the diff. Okay. Now, in order to recognize E, we're going to have to do something a little bit more. Yeah. Int E count is 0, and we'll do, let's see here, if last C equals 0 by AT. Okay, how are we going to do this? E is, what does E look like again? Echo. So first we don't want to recognize A, right? We don't want to recognize A. So we can go ahead and go do, but what we could do is we can look for E first. So hex dump again. Let's do hex dump. Look for 8.4. Okay, so E has 8.4. We can just look for 8.4 first. If C is 0.84, then you can do E count plus plus. That will kind of work. But it's going to count both characters instead. Okay. 84. Oh, why did it count 84? What is the test output? Ah, 84. That's strange. Why didn't that work? E count 84. That should have worked, from what I can tell. Edit test input test hiragana E. Oh, because it's not actually writing it down here. That's why. If E count print kana stats line to E count 0 total. Okay, it's not going to work because I didn't set the total line. Total. Okay, so it's showing me E, and the total line at the bottom is correct. Test out. So E. Okay. I think it's easier to read if I use a unified diff. Context length. Yeah. Okay, yes, it adds an A. So, great. So we basically don't want to recognize the A, so we'll have to do end last C is 0 by 80. What was it? I forgot already. Hex dump 81 and C. Oh, but wait, that's not what we want. We want last C is 81. So what is A? Again, 81. So both going to have last C equal to 81. So what we do is so A is no longer distinguished by 8.1. So we do 8.2 instead. But that's probably not going to work either, because I bet there's other characters with A. So we'll just do make kind of stats test and do a diff. Oh, didn't work. Diff. Test dot c dot hiragana e dot test. Okay. Still has an extra A 8.2. Oh, because Mo has an 8.2 inside of it. So we'll do last C is 0 by 8. What was it again? Hex dump. Hex dump I has 8.1 as the last C. Okay. So does A. Okay. What happened? Kana count is too low. Okay. Good. So we do total plus E count. Okay. kana count. Okay, here. Plus E count. Okay, getting closer. Oh, I added it in the wrong spot. We want to add it to the hiragana total. Plus. Okay, so what we want, I think, is we need to fix the way we're counting the total. So we want the hira total to be that, and the hira total is that. Okay. Hira total. No. We want hira total. It does not have this one. Gotta count. Okay. Hira total. Hira total. Plus. Okay, so now we're not adding stuff together so much. Hira total. Okay. Let's see what happens. A kata total. Still getting a 0 for the katakana count. What is the actual test? Oh, did I get an error? Total undeclared. Oops. Total, hira total, and int total is 0. Okay. Good. So now, So by the way, in order to actually test that total is not an int64, we're gonna have to actually write like billions and billions of items to the kind of stats. That's not really good. That's not good at all. So we're probably gonna have to change that manually without using test-driven development. So the test passed now, and we're this is looking kind of ridiculous. So we can look at the test, look at the code rather. Everything looks pretty good. All right, and so next, let's see if we can get a kanji that conflicts with a, that has 8-2 in front of it. So we do hex dump of a, and let's do printf e4 8-1 8-2. Let's see what that is. Okay. That I think that's unusual. Okay, but anyway, there's a kanji character we can use. So we'll edit. Let's open up kana stats test. Oops, I did not copy that apparently. And shares the first 2 bytes with. Oh, wait a second. Here, I didn't have the correct comment. E shares the second byte with a. It looks like. The comment's not correct. A1 first 2 bytes. Yeah. Shares the last. There's the last 2 bytes with Okay. Good. So we'll do kanji shares last 2 bytes with hira a. Okay. So let's copy this. Let's edit test input / kana stats test.c dot this, and we'll paste this kanji in. Right, and we're going to copy the expected test out of kana stats test dot empty input to expected test out slash kana stats test dot kanji shares last 2 bytes with hira. Right. Okay. Now let's run a test. Kana stats test. Now we're going to get a failure here. All right. Thinks there's an which is not correct. So that means we have to do last C is 0 by 83 and okay. Good. Now I do make good, that works. So I see a pattern here. We could just change check for last C at the start. So if last C is not equal to E3, then continue. Or no. Here we go. This should work. Delete. Okay. But this is kind of an empty win because we really just want to be comparing the bytes exactly. So what we can do is we can we could just switch to using the hash map at this point, and we can also use like all the hiragana in a single test. So we do test input slash kana stats test c dot lots of different hiragana, right? And we'll do iu e o ka ki ku ke ko and sa shi su se so and ta chi tsu te to. All right. Now this is going to be a bit of a pain to make it work. So let's create a hash map now at this point, because that's the easiest way to track what characters we have. Anything else is ridiculous. But anyway, let's do the kana stats test change. So we have, let's see here, start test file. What's different hiragana? Okay. Here we go. Test input, that file's not found. Okay, so we're going to create a test input file. Oh, didn't have the last there. Okay. Do is enter. Okay. And let's also fix this. We didn't name this properly. Oh, crud. I didn't change the right file here. Here. What I wanted to do was write this into the expected test output file. So we'll do this expected test out kana stats test.c dot lots of different hiragana. Test out. Okay. Great. So I'll make. Okay, so the missing test file is not the problem. Okay, so we're close. We're not that far off. We did find lots of characters here. So what we're going to do is we're going to say here we'll do the kana stats. Let's see, and we'll have a hash map. So we've got now. What's the easiest way to populate this hash map at first? I guess it's to use the Romaji information. So that would reduce the amount of like redundant work we have to do. Yeah. So let's do that. Let's see. Collect potential mappings, struct maps, struct map stats, potential mappings, and delete this when we're done. Okay. And right, so now we got to set the Romaji config. We're not using CLI flags. So romaji.h. This has okay, Romaji config. Classic woe, I guess we'll include classic woe. And no include kanji numerals. We'll do classic woe is 1. And dot include va is 1. And I guess we can do dot wagyo with dakten is 1. Okay. Or we could just comment that out for now as a note that we want to get that back. All right. So we have I. In fact, let's just comment this out as well. So Romaji config, include kanji numerals, that's fine. We don't need to do that again. Get Romaji codes, input mapping, destroy rate input mapping, in a hash map. Out with input mapping.count. And so then, yeah, we will, let's just change this to like 20. And maybe 40 to do find write capacity bucket count. And convert mem copy conversion. Okay. Then we'll do hat insert. Let's see. Don't remember my own API. We have find hash map entry in out, and the key is called conv, and the found key is found key and found value. All right. So we'll do char const, or no, char found key, and then the found value is what? It is a kana counts thing. Struct kana counts, but I guess we're initializing it to 0, so we don't have to really do anything about that. So we'll just do void found value there. Okay. Then we can do mem copy found key equals con, and that's size of con. But do we need this? Do we need this if we're just copying it from input mapping.l? I think not. So find hash map entry. What is it? It uses size of the hash map keys, so I can give it something that's not really correct. I can give it a char pointer. It will still work, I believe. So let's get rid of that. Char times key is input mapping.l I dot orig or conv. Yes, conv key. Okay. Key. size of conv. There we go. And right, so now what we'll do is we'll have a buff of 3 bytes, I guess. So instead of last C and stuff, we'll have char buff or conv or ridge. And because what are we going to look in the map? We're going to look up conv in map. So conv. So then we do conv. Oh boy. Okay, so do find. Okay, how do we want to do this? So we don't want to conv to get very large. We don't want to fill up capacity just without it being intentional. And in fact, for now, it's always going to only be 3 bytes. So let's just approach it that way. So we'll do conv and equals last C and last C and C. Then we're going to say find we'll do what is the hash map value? Struct kana counts. Kana counts count is nothing. So we'll do find hash map entry, and we look for hash map inside of, what's the hash map? Stats. And we look for the key, which is conv. And then we look for, we give it the found key, which is, I guess, whatever, something or other. And first I'll write down count. Okay. Then found key, char const found key. If okay, actually we want this down here after we check for end of file, and we say if found key 0, then we don't have anything to do. Otherwise, we do a found key dash hiragana count. Oh yeah, here's a tricky thing. We don't actually want to use the katakana count yet, so we'll just say here. Instead of kana counts, we'll just use the uint32 count or uint64 type values. Okay. Found value and okay. uint64t count. And then count key. Do count plus plus. All right. And oops, I didn't mean to do that. And then we also have to add the total total count. Total plus plus. We need to check if it's hiragana or katakana or not. And we don't need mo, ro, I, and kata count. Okay. So we'll do uint64t, hira total, and kata total. Okay. UN64. Now we also have to handle katakana, so we can do if total here uint 64t total. Okay. Total plus plus, and then we say if not stir cmp of and conv, then we do hira total, otherwise kara total. Okay. Total is counted already, don't need it here. And now we're going to do this in a loop. So, yeah, but we have to do it in order, don't we? So we could go ahead and let's see, how do we want to do that? We're going to have to do a binary sort, I suppose. That's a bit of a bummer. Because we were using a hash map, now we have to create another thing for the array to store all the values. So maybe we actually do want to use an array and not a hash map, actually, which is kind of sad. But struct stats map, we can call it, let's see, struct stats entry, and we'll do conv. So we could just make it do a char const conv, because we already have the domaji config. Oh, but we're gonna get rid of the domaji codes by the time we return from here. So no, it's not gonna work. Do conv kana and uint64t count there. So then we want to do a struct. So we're going to have this struct stats entry elements. This is just an array, size t l or count, and size t alloc. All right. Struct stats map stat and collect potential mappings. Stats map out. Okay. So we don't have to init the hash map here. And we will just go ahead and do the input mapping. So we'll do alloc grow by, wait, does alloc grow by increase the count or just the allocation value? Alloc grow array by, oh, I see. Okay, let's just keep it as it is. So grow, oops, grow array by. Array is out, or rather out, grow by 1. And yeah, so now we'll do a mem copy from out l out dash cnt on yeah. Struct stats. Do we want to save that? I guess we don't have to. Mem copy is input mapping.li.conv. Okay. And size of conv. Okay. Great. And then okay, so the count should already be 0 because that's what grow array by does. So that's all we have to do. Now, down here we got to do a a stats test. So let's see, stats entry. We want to get a stats entry value, so we don't need found key or count, but we do need a struct stats entry, and so we'll do a binary search, b search, and the LME is what we set the found item to, actually an index. So we'll say, oh, but I think we b search index, b search. Oh no, b search index is if we want to use the index. So we don't need to use the index. We just need to know if it's there or not. The index is the b search index is in case we want to we want to figure out where to insert the item if it's not already there. But that's not what we want now. So we want to go ahead and do b search entry finds in stats.element, count is stats.count, and comparison is strcmp. What is CMP? CMP is a function. I mean, does it return? Okay, it returns negative 1, 0, or 1. Okay, so the we return. Let's see. We compare. So if it's less than 0, that means we're going to look in the lower part or the upper part of the array. So that basically means we put what we're looking for first, and then, right, because then it's going to be negative. Yeah, we put what we're looking for first, which is conv, and what the current element is index. How do you know what index is? Index count. Entry. Entry dash kana. That's what we currently have. Okay, so if entry, then we don't have anything to do. Otherwise, we say entry dash count plus plus. What was that? Total. Okay, we still want that. So entry dash, let's see here. Entry dash kana. I went blank there. So then kana total increased. Okay. All right. So now we want to go ahead and loop over every item. So int I. So for I is 0. I is less than stats.count, I plus plus. Then if I stats.l I dot count, if we don't have a count, then we continue. Oh, but do we really have to even do that? So we could just say here. Okay, so we're going to check kana again. So int is kana, char const c, and here we'll just say return not strcmp and entry dash kana. Okay, and we're going to fix that eventually. So is kana and entry dash kana. Okay. Then if is kana. Okay. If is kana c stats.li.kana. Then we continue as well. Because we want to put the two versions of on the same line, as well as the other katakana, obviously. So, okay. Now, now we're going to print the stats line. So we can do conv katakana, and then we'll just say mem copy katakana is stats.li.kana, right? Size of katakana. And so then after that, we're going to use that to get the stats as well. So we'll do like katakana. Oh, do we need to actually? Yeah, we need to convert it now. So hiragana to katakana, katakana. Oh. Then we do a struct bsearch conv entry dash kana. Okay. We do. Then we want to get the stats entry of katakana. Struct stats entry kata entry. So then we'll do another bsearch kata entry stats.l stats.count and compare katakana with kata entry dash kana. And if not kana entry, then it's probably a bug, at least for now. Kana entry for and stats.li.kana. Okay. Because basically, if you can type in hiragana, you should be able to type in katakana, certainly. All right. All right, so we're getting closer. Now, if not kata entry, otherwise, we're gonna print kana stats line stats.li.kana, and the width of that is going to be 2. We'll just assume 2 for now. And then stats.li.count, and then otherwise kana entry dash count, then total. All right. Then we shouldn't need any of this. Total, hita total, and then we have kata total. Right. Let's see what happens. Lots of errors. Okay. 37 mem copy. Incompatible type for argument 1. Expected very strict, but argument is struct stats entry. Okay. Let me do that. Try again. Is katakana. No previous prototype for is katakana. Static. 44. Entry is undeclared. Right. C. Kana entry undeclared. Yes. That's typo. Free hash mount dot keys 206. So destroy array instead of stats. Okay. Looking better. One char. Okay. Let's see what we did wrong. Okay, it's not finding it. Entry.count. Oh, we don't want to continue here because we need to, here. We can continue, but that means we have to set the last items here. Okay. All right, let's see what happens. One char is still broke. Okay. So, no items at all. Okay. Char, let's see. Okay, let's see what's going on. Conv. Looking up conv in the search entry. Oh, we didn't actually sort this. So, do we have a sort? We should have a sort here. Qsort. Qsort PL. Okay. Qsort. The prefix we don't need. That P thing is something I never really needed, I think. What is P? Yeah, don't need P. And P is just, I put it there because I thought I needed to disambiguate symbols that appear in the outer scopes. And so that P was prepended to any kind of temporary variable, but I don't think that's necessary at all. So we qsort P, L, count, and less than. Okay, element is, what is EL? L, pivot size of L. Elements is the list of things, so out dash L. Count is out dash count. And less than is, so we're going to have A and B, I think. So we do a string compare of out dash L A and out dash L B is less than 1. Okay. Let's try that. Less than dash L dot kana. Let's try that. Okay. Still not working. Okay. Get Omachi codes, init put mapping. Okay. Using this string compare. When you do a bsearch, let me see what how bsearch is working usually. Bsearch, we pass it. When we do string comp, we pass it. We pass what it's looking for last, and the result is first. Okay. Okay, let's try that again. Oh, but wait, why is that different? Yeah, I'm kind of confused. I thought I figured that out right, and so less than means entry is what being considered, right? So entry. So now if entry is too low, then we set min equals, okay. Then we set min higher if entry is too low. That makes more sense. So let's see. Okay, which test failed now? But got no kind of entry for ah. Okay. No kind of entry for ah. That doesn't make sense. That's kana. Kana, then. So, why is that? So, apparently it did count ah properly, but the katakana version of it is not being found in this map. Bsearch. Oh, did I screw up bsearch again? Yeah, that's why. Okay. kana. Okay. All right, let's see now. Katakana. Okay. Let's see what happened here. Oh, it didn't find okay, so so this is not what we want exactly. We first check if it's katakana. Then if it's not, then we also check the we also find the hiragana, right, down here. And if we have no hiragana and no katakana, count. Oops. Let's see. Hiragana dot count. Let's see. I went blank again. Where is kana? It is kata and no kata entry. All right. So the count. Okay. No kana entry for little a. No. That should be supported with XA. No kana entry for little a. Not kana entry. Oh, we're not detecting katakana properly. Good. So we can fix that right away. So I guess what's happening is it's seeing is katakana is false, and then we are converting this to katakana, and it's gonna should be the same thing, right? So no kana entry for this should actually say no katakana entry for katakana entry. But why is hiragana to katakana acting funny for that should work. Edit hiragana. Okay. Edit romaji.c, I guess, is where it's defined. Hiragana to kana. Okay. Oh, maybe this is not working properly. Edit hiragana. See, H2K test. I don't think little a is working right. Oh, because it's okay. So we actually need to check something else. So we need to check the range here. Here we don't want to do anything. So what's happening is hiragana to katakana always is going to screw up its input if it's currently hiragana. So what we need to do is we need to go ahead and say in other words, if it's not hiragana, it's going to screw it up. So we want to actually check the code. So chars.c code point range. If it's hiragana, let's see here. If code point range of that is not equal to code point range other, not equal to hiragana, rather, then we continue. We don't want to do anything about that. Okay. Code point range. Okay, so now we input chars.c. Oh. I'll include chars.h. Okay. Lots of different hiragana is the one that failed. Good, so we're getting closer. Okay, wow, that looks very good. So we did have 20, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, yeah, 20. So, okay, this is the correct output. Definitely. So let's go ahead and save that. And We're getting closer, I can see. So let's do chars dot, let's do test, or kana stats test. So one problem is that we have to actually copy the correct test output here. All right, make. Good. Okay, so other katakana, katakana. Okay. So let's do cat test input katakana stats test dot lots of different hiragana. Okay. Then we do new sort HTK. Good. That worked. Do test input kana stats test.c dot lots of different katakana. Okay. Now let's see what happens. That's probably not going to work. I mean, it's really not going to work at all. Kana stats.c. Kana stats test rather. Kana stats test. Lots of different kind. Okay, I already declared the test. So let's see. Okay. Oh, this did work. This did work somehow. I don't understand. I don't think I used the right logic to check for is katakana. Oh, the total is not correct here. So and all the total is in hiragana, the hiragana column. So we want to do let's see, code point range equals code point range katakana. Okay. So we can do switch maybe and do an error for the other stuff. Case code point range katakana. Case code point range hiragana. Total hira total and default. Need a break. I forgot about that. And the default is bug. Should not get here. Only processing kana. Okay. All right, let's see what happens. Is katakana is not used. Okay. All right, now what happened? Test output. Let's see, this is probably correct now. Let's see though. Good, that's correct. So now we can save it. And at this point, I feel like we're at a pretty good stopping point. So, there's a bit more to do. So we don't support things like this kyo. In other words, the kind of kana sequences that have 2 in them, like this. I don't know if you can see that, but that's probably going to connect. We also have to figure out classic wo and include va, but that's going to be very simple. That's going to be trivial. And yeah, so this is surprisingly workable, despite like a lot of having started out as hacks. And this is I guess a good demo of test-driven development. Maybe you could have done it faster, but I don't know. I did it pretty slow, and it felt pretty slow. but at the same time, I'm confident that the code is actually pretty clean, relatively clean at this. Once I've worked through it enough, once we've kind of hashed over the simplifications, I know that the code is pretty clean, and that I have confidence that it's working very well. Um, so we do still test for like non-kana, so that's good. I'm disappointed that we didn't need the hash map, but I have a feeling the hash map is going to come in later at some other time. And it's actually not bad to have these utility functions that you don't really use very heavily, or you feel their just existence isn't justified, because it does let you do development a bit more flexibly later, because you can just, like, as you're prototyping, you can just kind of add it in. You can just kind of start using it without holding back or anything. And so that's something I've realized when doing this. But other things I've realized is that if you're not really sure exactly the details about how the code will look, sometimes test-driven development will make it will help you out. It'll kind of give you some guidance as to how to write the code and how to shape the code. Like, if as long as your overall algorithm is not too is more or less decided, then test-driven development will get you to like a kind of a clean representation of the code, and it's incremental. You don't have to know what you're doing at the very start exactly. It leads itself to incremental coding and improvement to the code. Um, and yeah, I'm gonna I need to think a little bit about how I want to support the things like kyo, or other words, two character sequences, and then when I do that, I guess I'll start the next video. But for now, I need to take a break, and and just think about this kind of offline for a while. Anyway, that's all, and thank you for watching.